Welcome to another discussion on electric machines and controls. So in the past, we talked about a couple of topics on permanent magnet synchronous machines and field-oriented control. What are the different aspects involved with field-oriented control for a PMSM or a permanent magnet synchronous machine? And in order to go into a little bit more deeper discussion and to implement the system practically, there are several subsystems that we have to understand. Okay, so if you look at the machine, of course, the machine design has a science behind it, which I don't plan to get into in this series of lectures. However, there are other factors associated with the implementation. You have to measure currents in order to determine how much of current need to be injected, and then of course we have the reference frame transformation, and then depending on the reference and your actual current, the PI regulators will determine how much voltage need to be applied using the inverter. So we have a three-phase inverter here. Okay, now so going forward, I want to highlight on three things. I want to initially look at the voltage generation schemes or modulation strategies that we come across. Then look at current measurement. There are a couple of different types of current measurements that we can use, and also position measurement. Okay, so those are the key things that we need to keep in mind. Everything else is basically algorithmic, which means it can be implemented using a microprocessor in the form of code. Okay, all right. So so these are the topics that I want to specifically talk about. So we'll start with voltage generation. This could pan out into a couple of different lectures depending on the level of detail we have to go into. So just keep an eye out for what comes up or what shows up under the on the channel or the playlist. Okay, and then once we are done with all that, we will go take a final look at the phase or the time domain relationship of the current, the voltage, the flux, and then also our position measurement and how all of that align in the time domain. Okay, all right. So let's get right into it. Now, of course, we are looking at a three-phase inverter. There are 5-phase inverters. There are 6-phase inverters, which are in different type of architectures. But for now, for the basic understanding, we will focus our attention on a 3-phase inverter. Okay, and in a 3-phase inverter, you are going to have switches. They are typically semiconductor switches, MOSFETs, IGBTs that are being switched using PWM. So there's a modulation frequency, very high frequency, like 10 kilohertz, 20 kilohertz, that these switch at, which you might be familiar with depending on if you have studied DC-DC converters, and or maybe DC machines, H bridges of that sort. Okay. And we have 3 legs here. We have 3 legs, and then we have 2 switches per leg. And we can modulate. So once the top switch is turned on, when you turn on the top switch, you will connect your power supply or the battery positive to phase A. And depending on the modulation strategy you follow, either one of phase B or C or both might be on as a return path, because we need a current to flow in a closed path. Okay, so we look at that in detail. However, we don't want to turn on both switches except for certain circumstances or certain cases that we might talk later. But when you have your power supply, and typically you have a DC bus capacitor that goes here to handle some of the switching transients, but Typically, you don't turn on both switches. If you do that, you're going to have shoot through. It'll short the power supply right through the switches, and that can damage the power source as well as the rest of the hardware. So we try to avoid that as much as possible. And depending on, like I mentioned, depending on the modulation strategy we plan to use, we can use a combination of these top and bottom switches to generate the current that we want in the machine. Okay, so essentially by modulating the PWM, so if you forget about these two phases or these two legs, let's focus on one leg. And if we can modulate this PWM such that we get a sinusoidal voltage, or at least a sinusoidal signal on phase A. Okay. Similarly, on phase B, we can apply a voltage that's sinusoidal in nature. Now, we need to keep in mind on the motor side, we have three phases, right? We have three phases. And when we talk about the voltage that we apply per phase, that is the phase voltage that we are talking about. We're applying that phase voltage, and the current will depend on the voltage, the phase to phase voltage that the three phases have, and the different strategies and to switch the switches can be discussed later. But we have to first keep in mind we're going to study how the phase voltage is generated, and later we can go into a deeper discussion on how the phase to phase voltage will result in the currents because of that closed path we have through the rest of the two phases. Okay, so initially we look at the modulation on half bridge, and of course, in order to generate that modulated voltage, or we will generate a reference signal, and it will get compared with either a sawtooth or a triangular wave to generate the PWM, and then the inverted signal of the PWM signal going into the top switch will be applied to the bottom switch with some dead time in between those two pulses to avoid shoot through. Okay, and when we do that, we'll be able to modulate a sinusoidal voltage onto this, and this is going to be, you'll see that this is a modulated waveform. I have a simulation that I can show you. This is going to be a modulated waveform, and once it passes through the inductive material, it will act, inductive elements in the machine, it will act like a filter, and it'll filter out the high frequency content, and in terms of current, it will look like sinusoidal. Okay, so I will have a short simulation showing the effect of that as well. Okay, so first of all, let's try to understand PWM generation, and I'm sure some of you may have seen this before. So if you have, feel free to skip ahead. We have a carrier waveform, or the waveform or the signal that we use to compare with. Okay, carrier waveform. This is typically at a very high frequency. I'd say 8 kilohertz and up. So it's probably going to be larger than 8 kilohertz typically. The reason behind that is you don't want to have an audible signal. That's one reason. And then as you increase your frequency, we know that our switching losses increase. So we have to manage the switching losses as well as the audible noise when it comes to certain applications. So keep that in mind. And first of all, we look at this triangular waveform, and we need to apply a reference signal which gets compared to the triangular waveform so that it gets converted to PWM. Okay, and typically if we want to generate a sine or a cosine signal, we will have a sinusoidal signal. Now, In practical systems, our numbering system, if it's not able to handle negative, typically we'll have the waveform or the reference with an offset. Okay, so it could be like this, could be like this, and everything is implemented in digital domain these days. So your variation of your signal could be from 0 to, let's say, 1023, and then halfway point is 512 counts. Okay, so that's the typical in terms of binary, right? Because you have 2 to the power number of bits for your register. That's how you determine how much peak to peak value you set. And so this the triangular waveform, this is generated using a timer, a counter that you have inside the timer unit. So essentially, if you look closely at this signal, this is a step incrementing stepwise, slowly incrementing step by step. Okay, and then you'll have a comparator inside your timer unit or the PWM generation unit, which compares your reference with the carrier or the module or the triangular waveform. And if this voltage is positive, the output of the comparator will go to high, or it will rail to the high side. And if it's negative, this will rail to 0. So which generates our PWM signal. Okay, so let's see how that will result in these two cases. So we are looking at two PWM intervals or triangular wave intervals. For this period, our SR, this voltage is what? It's going to be negative, right? Therefore, we will see a 0. Is it? No, wait. No, that's SR. Yeah, SR is positive, right? So it's larger. Therefore, we're going to see a high in this case. So this is 1. And then this is, after that, our carrier is positive. Therefore, it's negative. This is negative. So this is going to go to 0. Okay. And after this point, so if we set this right there, after that point, for the period from here to here, again we can see our reference is larger. So now we can set, we'll set the comparator will set the output to high for that period, and then again for the short period, the output will go to 0. Okay, so this way, this will now continue depending on how the reference will change. This is a little bit of an exaggeration. In practice, with respect to the carrier, your reference is very slowly changing. Okay, and we'll see that in our simulation as well, because we want to generate a fine enough of output voltage using the carrier wave. Okay, all right. So, and all of these are going to be implemented in a digital. If you are using a microprocessor, it'll happen in the digital domain. So you have to pay attention to your maximum value of your reference signals, and which will ultimately result in the PWM values. Okay. For theoretical analysis, generally we use 0 and 1 for these. 0 and 1, and sometimes I've seen people use -1 and +1, but just keep in mind, in applications you need to set or define what 0 is, define what 1 is, and adapt your algorithms accordingly. Okay, so this is a triangular wave, and then these are. So this is another form of a carrier that you will see. Again, this is the compared, or the carrier wave that we compare to, and this is our reference. And these are edge aligned. You can see that it's aligned to the edge, and we have the previous one, it's center aligned. We call it center aligned. Okay. And here again, you see a similar nature. we have, so you can see that the PWM is growing because our reference is again increasing, right? So reference is increasing, therefore the amount of PWM, the pulse width, is growing even though the frequency stays fixed. Okay, and then same phenomena here. There are different slight difference, different advantages and disadvantages depending on which method you use, center aligned or edge aligned. And so it's good to know that they do exist. Okay. All right. Yeah. So we talked about the differential voltage that we see, right? So each phase you will see that we apply a certain voltage here as a modulated. So if you are to see this, so I'm going to exaggerate a little bit. So you might see something like this. So maybe like half sign there, and then your phase, if this is A and if this is B, then you're going to see a similar waveform but 120 degrees out of phase. Okay, so maybe somewhere here. So you'll see, and then that differential voltage is what results in a current. So we have to think of that phase-to-phase voltage that we apply. Okay, and then you'll see the current. Typically, this voltage is at 0, or we call that kind of a virtual ground there. Okay, let me see. Yeah. So before we move on to my simulation example here, let's look at the different strategies, the modulation strategies that we have. We have sine triangle modulation, which we will look at today, which is basically we have three waveforms that are sine or sinusoids that are compared to a triangular waveform, and then which results in the PWM signal. We have a third harmonic injection scheme, which has benefits. It'll provide the ability to increase the amount of voltage that we apply to the motor, to the phase as a phase voltage. And then, so the third harmonic injection involves injecting a sinusoidal third harmonic, and then the simplified third harmonic is a little bit simpler to implement. It's injecting a triangular wave instead of a sinusoid. So computation wise, it might be a little bit simpler. And then of course, the very common space vector PWM. Space vector PWM is another, it's using the space vector method to come up with the pulse width modulation strategy. So it's a direct, it'll enable us to go from a space vector calculation to a PWM time, on time, off times, in a methodical way. And then discontinuous PWM is, it has its own advantages to minimize losses by holding some of the switches on all the time while others are being modulated. Okay, so we can look at all those, at least some of the key modulation strategies in our discussions to come once we build up the background of how sine triangle method operates. Okay. All right. So with that, let me switch to my simulation. All right. So I hope all of you can see what I have here. So here I have a repeating sequence which is acting as the theta that we apply to the machine, which we typically call the converter reference frame. In a closed loop system where we have field orientation, typically we want this position. This is our position signal, and we base our voltage that we apply based on that position signal, because we want to align how we apply the voltages so that the currents are going to be aligned to generate optimal torque, right? We have discussed this in previous discussions. Now here we are just looking at a very simple open loop configuration, so no closed loop, and I have I have three of my sinusoids here, and you can see I'm targeting a practical application, so I have an offset of 0.5 in each of them, so that they are not they don't have a negative component. They are all going to be positive sinusoids. Okay. And then here I have the amount of modulation I can apply, the level of how much of an amplitude do I want on the sinusoidal voltage I apply. Okay, so the modulation is going to be around 50% duty. If I want positive voltage for a phase, it will modulate above 50%. If I want negative voltage, the PWM will go below 50%. And now with respect to another phase, you will see either a positive or a negative voltage, which gives me my sinusoidal outputs for the machine. Okay. And see, I have the three voltages, and those three voltages here, what I'm doing is I am modeling the switches, kind of a pseudo model, this is not a true model of the switching, because I don't have all the nonlinearities here. Basically, we have a repeating sequence here. This is a triangle wave, and I'm comparing my reference. You can see that my reference is being compared to the triangular wave, and depending on what that difference is, the switch will either it'll be either set to high or low or zero, high or zero, 1 or 0. Okay, and this is for phase 1 or phase A, this is for phase B, this is for phase C. Now once I have that PWM, I have a sim power voltage source here that will convert that to an output voltage which applies to my load here. So this is modeling an inductive load, which is close enough of a machine. I know we don't have back EMF of that in here, but this is good enough to get the idea. And we have the three sources that are resulting, or that are converting this simulation output into a voltage that applies into this load, inductive load. And we can see the current outputs here, and we can compare how the different waveforms look like. Okay, let me run this simulation quickly here. Hopefully it doesn't crash. And later so this is using the sine triangle method. We can compare different strategies in a later video, once we go through and understand all of them. Okay, all right, so let's see. First of all, let's look at these three voltages, or the three reference signals that we are applying. Okay, there we go. So you can see we have three sinusoids, cosines, to be precise, cosines that are 120 degrees out of phase. And then we can look at the current, right? So ultimately, the voltage that gets applied is going to be PWM, it's modulated voltage. However, when we look at the current, you will see that the modulation has been removed. So it's filtered out that frequency component because of the time constant of the R and L because it's acting like a low pass filter. So let's look at all the signals for phase A together here. Okay, so this is my carrier wave. Let's make sure that's my carrier wave, right? So this is my carrier wave, and this is my reference. This is my reference. This is the PWM signal that results because of with the comparator. That's the comparator output. So you can see it's 0 to 1, and this gets converted to a voltage that applies to the sim power load. And once it passes through, we can see that the current has a nice sinusoidal shape. Of course, there's going to be somewhat of a phase shift between the voltage and the current because of the inductive lag. Right? There's an inductive lag that results in a slight phase shift, which is true for any machine. In certain cases, we tend to compensate for that, and we can talk about that later. And now let's zoom in a little bit. I want to see, what is actually happening here. So let me try to zoom in a little bit, hopefully. Okay, there we go. See, we can see our reference signal varying like that. And then so proportional to that difference between the two, the pulse width is also changing, right? So the pulse width is also changing. Around 0, it's going to be at about 50%. And we can see the filtered current here. So there's somewhat of a ripple on the current. It's unavoidable in practical systems. This is much more prominent than in the theoretical world, in the simulation world. But it gives us a nice comparison to see what happens, right? So this is what will happen, what you will see in PWM inverters, especially three-phase inverters. And if you compare all the three phases, you're going to see similar characteristics. So if you want to compare, let's say, phase B and phase C currents. So let's see if we can run this quickly. And let's convert them to 1 if we could. Yeah, so there we go. So the three currents are 120 degrees out of phase, and we can see that here, right? So which means we can generate current, and you can see the ripple a little bit more better in this case, which proves us right? So now we can show that with sine triangle method, we can generate voltage or current. And if we are to go look at the voltage that we apply, I want to see right here. So this is the voltage. No, we'll leave that for now, because we do need to filter it to look at the voltage. Right now it's modulating voltage, right? But the key point that we need to remember is, so we are applying 0 and 1 either. So 0 corresponds to 0 volts coming out of your battery. 1 corresponds to the DC voltage, the DC bus, right? For our converter, the center or the middle of that is at 50% of your DC bus, which is half your battery or half your source voltage. That's your 0, right? In order to have a positive and a negative, your half VDC becomes the 0 point. With respect to that, you have a negative voltage and a positive voltage, which means the maximum phase voltage we can apply with this method, at least for now, we can see that is half the bus voltage, right? Your sinusoid, your peak-to-peak value of your sinusoidal voltage will be VDC, which means the peak value that you can apply is half VDC. Okay. In later, we'll come up with a modulation strategy, or we'll at least show that we can improve that a little bit with this new or proposed modulation scheme. Okay, so that's in the future. So for now, we will stop the discussion on the modulation strategies. Hopefully this gave a concise idea of what we are planning to do. Next couple of videos will be focused on either one or two specific modulation strategies and how are they implemented. What do we need to do to implement them, and how do they function? Why do they function? And we'll try to answer questions like that. Okay. All right. Thank you, folks.